Windows works or something. That's like the only way to contact people.
Okay, welcome back, everyone. I guess today is a party day, but some people are here, which is good. And I hope someone's like, yeah, I'm not here, I'm actually skiing. But that's okay. So those choices we have to make not to ski. So today our topic is interrupts and exceptions, right? And I was mentioning interrupts in passing many times, right? But today we finally get to the point of understanding why we need them and how they are implemented. Let me actually stop here for a sec. So are there any questions about the homework or hello world? Because I was overhearing some conversations that things are not working well. Yeah.
So I don't know, I think Weemoo, there's the final step on your website, the guide, has this setting up path variables, I think. We S6 with the K lab, I think we're in a different CSH instead of bash.
Oh yeah, so just type bash command.
Okay.
I mean, it's the same for me. And like historically, like let me show you what I do. Historically, so supposedly there is a way to set a default shell, and I forgot what it is. But when I just go there, I'm also in a shell in a TCH. And I just do bash and I enter bash, and now I'm bash. So I mean, it just works better for me this way. Like what I did is just I type bash. They have bash, just that they, for whatever reason, they set the default to a different shell. Maybe Kachang knows better how to change it. I don't remember. I haven't done it in many years.
I also just type bash.
Is that a problem? Now you're good.
Yeah.
And just like yeah, in this, I forget which one they use. Do you remember what shell do they use? Yeah, so yeah, this one shell is defined as TCH, and I like to define an environment variables. There might be slightly different syntax for that. Stream is not going. Oh, that's good. So why is it going? You sure?
I'm seeing people on Discord say that.
Oh, you have a Discord.
Well, it's just friends. Yeah.
That's good.
Oh, he said it showed up.
Huh?
He said the stream's going now.
Okay.
All right.
Yeah. So back to TC shell. What it like I probably say something like what is x6 setup instructions somewhere here, or specifically for the something along the line, it's like something like export the paths. This.
What does exported path mean as well?
It means that if I, for example, do this env command, which defines my environment, okay, so it's a mechanism to slightly reconfigure your environment through those variables, which you can define and redefine. And path is a variable which tells the operating system where to search for binaries. Like, you know, and my path right now, if I do something like env grab, path is defined to be this. So it will, when I say something like ls, right? So this ls command, I did not specify the absolute path, which is, if I say which ls, it will tell me that it's inside bin, right? So really, shell doesn't know where it is, right? But shell will consult my environment variables and say, okay, I will search in this order. I will search in user local as bin, user local bin, user as bin, user bin, as bin, bin, user games, UUSOC bin, UUSOC bin opt. And where's my lovely bin? Bin is here, right? So that's why I actually can find this ls binary, right? And if you compile your own binary, like by default, shell doesn't know where it is, right? And so this is what I'm saying. So I forgot if I did it for myself, but when I entered bash, I put this, if I do it again and grab paths, when I did this installation of QEMU, right, I added this to the path, right? And that's why when I type something like QEMU, oops, sorry, whatever, yeah, it auto completes for me, but and that's the step which I'm trying to. The reason we did it is just we need a slightly specific version of QEMU, right? So let me show you here. So projects probably. And what is it? No, so this QEMU. Why? If you like, there is like support for a couple of different things, but what we're critically looking for is for this. Okay, whatever. Probably not show you what I wanted to tell you a story, but the story is that this guy, Cody Cutler, who was an undergrad here in Utah, and he graduated and went to MIT. So he did this patch. So for this version of QEMU, when we're going to boot, it supports dumping of a page table, so which simplifies debugging specifically for the homework which we used to assign back in the days. We don't assign it anymore, but it's still useful for this Hello World homework, because there will be a special command in QEMU which allows you to please show me the page table. And that's helpful because sometimes you don't know what it is, right? Because when you define your own page table, I can maybe elaborate on it a little bit more. And that's why we need it. So we would be fine with a stock version of QEMU, but that's just useful. And an additional interesting bit to this story that Cody is actually back to Salt Lake City, I think this Thursday, because we are celebrating 50th anniversary of the School of Computing, and Cody got invited as one of the speakers. So I haven't seen him in a while. So he's a nice guy. So please go and attend one of those celebrations. If you never heard of it or just 50th, I think it's worth attending at least some of those talks, because the people who are presenting are just world caliber researchers. Some of them are with Turing Awards and like co-founders of Pixar and stuff like that, right? So it's it makes sense to make sense to attend. Let me just specifically what there was a schedule on which I saw Cody. It just, again, maybe here. He was invited as a panelist. I don't really know if he's attending, but I hope he is. Probably I'm not sure, but I mean, I've seen him on the schedule. I should probably touch base with him to figure out if he's really here. Again, why did it tell this story? Probably to inspire you that you can spend time here doing some research as an undergrad and then go to MIT if you want. When Cody was graduating, I think 2 students went to MIT. Were accepted to MIT. One went to MIT, Cody went to MIT, and another student, Grant Ayers, I think, went to Stanford just because he wanted to do more of a engineering side of the things. And Cody was a systems researcher, security researcher more specifically. And he built a new operating system in Go, actually, as his thesis. Was exploring how you can actually get a hold of a garbage collector, because if you listen to me a little bit more, I keep saying Rust versus C, because C is unsafe, so you introduce a lot of vulnerabilities, the kernels are exploitable, safety is important because literally 70% of vulnerabilities or bugs in the kernel which can be exploited are safety related. So when you just simply switch to a safe language, those just disappear. It's not my observation, it's my observation from Microsoft Research, who studied their low-level systems code base and just came up with this conclusion. And you say, look, let's switch to a safe language. And Cody was saying, okay, I'm gonna build it in Go, because his advisor said, okay, we're gonna use Go. And it was telling back then, it was maybe like 5-6 years, like maybe 7 years ago. He was saying, Cody, like drop Go, let's switch to Rust. But he built one in Go, and it's called Biscuit. If only I can type Biscuit correctly. That's the OS. And the idea was to say, like Go, like any other garbage collected language, enforces safety, meaning that you cannot access an object which got deallocated suddenly through a garbage collector. And there are like inherent overheads to that, because you have to scan the heap and figure out what's going on. And they were essentially trying to figure out how to tame it and essentially make sure that the garbage collector doesn't introduce too much latency to the kernel. And those guys, obviously, Franz Kashuk and Robert Maurice, if you carefully look at the x86 code base, those are the guys who built it, right? So you understand this, right? These two guys. And Russ Cox, do you know Russ Cox? He's one person who actually joined Go team, I think, at Google. So he is one of the co-creators of Go, right? Just a little bit of this genealogy, right? Just to make sure that people are connected. And back then, 6 years ago, I was kind of like low on resources. I was still a student, or I was maybe starting as a researcher, and I didn't have a team to build a system in Rust. So it took me some number of years, like 4 years, let's say, to like establish myself, find a team. And we built a operating system in Rust, which is called Redleaf. That's the page with my students. So again, a lot of undergraduates as well. And I think that that Rust is still a better answer to systems problems than Go, but still, nevertheless. Okay. Question.
I think the U.S. government also has started recommending people to not use C and C++ and those type of languages. If I remember correctly, there's a few different government agencies that have said don't use unsafe languages.
Right. Yeah, you're right. Yeah. I mean, so, but what name did you mention, or name of the agency?
I think it was I can't remember exactly. I think the Department of Defense may have, and I think it's also like the federal, one of the ones that's for. I can't remember.
No, that's true. And we maybe if we have time towards the end of this class, we'll be able to spend some time talking about safety and how can you build an OS in a safe language. But okay, let's see. Okay, good. Did I answer the question about the homework? Okay, good. Yeah, so come see Cody, come see those speakers, check this school anniversary schedule. There should be like a lot of interesting things. Okay, but that's the reason. But you really don't need anything, I think, from the Kate admin stuff. You can build everything locally in your home folder, and just use that copy. Okay, let's switch back to interrupts. Despite the fact that it's exciting to tell stories, right? So let me tell you the story of interrupts. Okay, remember where we are. Like again, my wonderful diagram, which everyone is tired of. So this is my main function in the kernel, and we covered these two wonderful initialization functions, right? So I ask a question about how many pages we have on the memory allocator after this kinit one returns, right? So just take a look at the arguments to make sure that you understand what is passed and how many pages are added to the allocator. But this is what we are studying right now, right? And we're making a slight detour because I don't see a good linear story for how to jump from here to the interrupts. I
jumping kind of forward, saying, okay, let's assume we initialize the kernel and even user level is running. So many people run processes, right? So today we're making this switch temporarily. And let's just see how interrupts work. And then we come back and I explain how we start the first process and how we initialize the interrupt descriptor table, which is relevant to today's class. But just there's this kind of discontinuity here. If I ask you a question again, so why do we need the interrupts? I keep mentioning them. So who will tell me the answer?
The only way the software side of things talk to the kernel, so you have to interrupt the kernel. It doesn't directly talk to it, but like it tells it there's something that needs to happen here.
Okay, so what you're saying is that you say, in order to invoke a function of a kernel, you cannot just simply say call whatever, sys open, right? That doesn't work. And we will explain, we'll talk a little bit more about why it doesn't work. But you say, right, correct. So I will invoke some kind of a thing which called int, which triggers an interrupt with some magical number. I will put XX for now here, and it will transition me in a kernel. That's correct. That's one way. Well, it's kind of a byproduct of modern systems. So it's not really the direct intent of using the interrupts. This is more of a secondary reason, because really, and on modern machines, instead of this int instruction, there is a different instruction, which is a little bit faster, which is called sysenter, right? Which also allows you to enter the kernel at a specific entry point. And I slightly touch base on that, but okay, still, it's a good reason. So you named the reason right. So, but maybe some other reasons.
Well, any function that I can see how that would happen, 19 call or resistor. But how about getting stuff from the kernel back to your system? Like when your program's running, you think you own the CPU, but how do I get data back there, like a keyboard press or like some signal that hey, it's your time's up, you need to let someone else take over.
Right. So what you're saying is that an interrupt, and this is the real reason why interrupts were probably designed in hardware, in CPUs, right, in the CPU interface, is to be able to preempt execution of a current program and switch to something else. And as your classmate is saying, those examples can be something like, I'm running for a long time, maybe I'm multiplying matrices, right? And I run, it's effectively like an infinite loop. It will run me for hours maybe. But once in a while, maybe you want to do something. And so you configure a hardware device, which is called the timer, to, let's say, 10 times per second or 100 times per second, send me a signal. And the signal, when I say send me, send the CPU a signal. And essentially, the signal is delivered through this interrupt interface. And that's why it's called interrupt. Meaning that, like if you're running your matrix multiplication code here, the hardware raises this interrupt signal. And there is a mechanism which we will cover today, interrupt descriptor table, or like in general, interrupt transition, which allows you to switch and start executing something else, like interrupt handler in the kernel, for example, right? And this was your user matrix code, right? And just to give you another example, when it's more meaningful, remember when we were loading the kernel, I was kind of like slowly trying to explain how we read something from a disk device, right? And surprisingly, we didn't use any interrupts there. We just simply said, okay, here's a command through this in-out interface. And you say, like, please read me a sector 55. And there was this instruction with a wrap prefix. Remember, we even searched online what this wrap means. And ins means read the in port in terms of longs. Long means 4 bytes, right? And we, in a for loop, we're reading this port. Like, remember, there was this in and out commands to access the ports. We were reading 512 bytes, right? So no interrupts whatsoever, right? But in practice, it's possible. So you can, it's called polling. You can poll the hardware to say, like, give me a byte, give me a byte, give me a byte. In practice, it just takes forever, because each of these in instructions takes roughly, like remember, you have to go through this PCI interface, remember the buses and everything, reach the disk, and then disk, which runs another CPU, maybe ARM, maybe x86, maybe RISC, which probably runs its own operating system or some limited version of an operating system, maybe processes this command and then replies. So it's millions of cycles, literally millions, maybe even tens of millions of cycles. And you say, look, just to read 4 bytes, I spend 10 million cycles. That's too much. And that's why people came up with a different idea. They said, okay, I will instruct you to read me 512 bytes. I will give you a pointer, you meaning I will give disk a pointer to read 512 bytes. And I will leave you alone. And you will do the reading, you will do the processing, you will send this 512 bytes back. And when you're done and those 512 bytes are ready, the disk will send the CPU an interrupt. And that's useful because while the disk is doing some processing, like for this, even for this 10,000 cycles, you can run a couple of tasks. Maybe your mouse will move on the screen, maybe you multiply half of your metrics, right? So this is an interface to communicate with devices saying, okay, I'll tell you to do something, and later on you will interrupt me when you're ready, right? And the operating system will process this interrupt.
So let's say, for example, you're trying to read like 1 512 bytes, like 10.4, can you do 2 512 things?
Mm-hmm.
Do you have to wait for one interrupt in order to schedule the next read, or can you schedule both and then interrupt and tell you which of them has to be?
Right. So in modern I/O interfaces, typically what happens is that there is a queue which sits in memory, which your disk can access. So this is your disk. And it can access this queue. Operating system puts requests into the queue with pre-allocated memory. The queue has some limited size, but let's say like 128 elements. So you can send up to 128 requests to the disk. And then tell the disk, okay, please process this queue. The disk then says, okay, I'll do that. I'll fill in those guys with data. And when I reach the end of this queue, only then I will send an interrupt. But it gets even more advanced at some point because network interfaces are so fast and modern disk interfaces are so fast as well. And NVMe is so fast that it can, if it would start sending interrupts on every packet, you would just simply just do nothing but process interrupts because the smallest 64 byte packet, network packet, can arrive literally like every it depends on the speed of an interface, but literally you can like expect the packet to arrive every 100 cycles, and it takes longer to process an interrupt than 100 cycles. So the hardware is designed to batch those arrivals, and then once in a while interrupt the CPU to say, okay, like I have enough, so pick them up.
So if it goes into, it will only interrupt at the end of the queue, does it create multiple queues so that it says, okay, do this, what we have now, and it has another queue that will move afterwards?
Not really. In most cases, it's just one queue and it's just half full. And there is the pointer, which is visible to the hardware, which points to the currently available element. And the hardware will process this 3, for example. And meanwhile, operating system might fill in additional ones. And the queue is kind of...
Trying to create a limit to say, okay,
yeah, these are available. Yeah, these are available, and it kind of rolls like a ring buffer. So when it reaches the end, it overflows to the beginning. And if there is no space in the queue, then you have to wait for the hardware. But typically 1 queue is enough. Although there are slightly different designs, but 1 queue is enough. I probably will try to come back to this, but it's kind of it's an interface of modern device drivers, or like disk and network. Okay, good. Okay, so this is reason, I would say, number 1 to interrupt execution asynchronously. Can someone give me reason number 2? There is yet another reason, which is kind of natural, but can be a little bit hard to guess unless you thought about it before.
To prevent just like error handling.
Give us an example. Like what?
Like when the user wants to access the exage memory.
Right. So, okay, let me repeat what you're saying. So what you're saying is that imagine we doing something like paging, and we say like we will page out pages from memory temporarily because we're running out of physical memory and we're going to save them to disk, right? And so, for example, the user tries to access one of those pages, which is not currently in memory because the operating system like took them down. So this bit, which is a present bit, is not set in a page table. It triggers a page hold, right? And this is handled. It's technically, it's called an exception because synchronous interrupts, synchronous meaning that the CPU triggers them. One of the instructions which you executes, for example, accessing a memory which is not mapped, or maybe dividing something by 0, right? Because like it's a bug. If you divide by 0, then mathematically your computation is not defined. So there is no good answer. You can return 0, you can return infinity because there is no definition for, there is no number. So if you say, what is division in general? So it's A by B, finding a number C such as that if you multiply C by B, you will get back A, right? But if you're dividing by 0, there is no such number which you can multiply. There is no C which you can multiply back by 0 to get back A, right? So that's essentially why division by 0 doesn't work, right? And so, and then you say, look, maybe I can fix this computation. Maybe I'll just kill it right away because there is no reason to continue. Maybe it was just a mistake, something like that, right? So essentially, this is error handling, right? And then this one is a third one. So it's used as a byproduct of those interrupt mechanism as a way of entering the kernel in a secure manner. To give you an analogy, it's kind of like a TSA checkpoint at the airport, right? So I was mentioning this in the past. You cannot simply invoke a function in the kernel. This is not allowed. But you can go through this checkpoint mechanism and say, okay, I really want to invoke this function. And if you're granted permission to do that, you invoke it, right? But this interrupt mechanism allows you to enforce this check. Okay, so there's 3 reasons, really. And historically, those interrupts, there was like different terminology. So synchronous interrupts were called exceptions. Something else was called a trap. At this point, I would say just don't bother. So just if you can remember interrupt or exception, interrupts usually refer to something what happens asynchronously. But if you use this term, it's just fine. So anyone in the community will understand what you mean, right? It doesn't matter. So you might be a little bit like, sound a little bit less professional than someone who can distinguish them, but it doesn't really matter because the same mechanism is used to handle all of them, right? And this is what we're gonna cover. So here, again, just repeating what we discovered on the previous slide. So 2 main reasons: synchronous, to correct from errors. So something bad happened, like for example, a program tries to access an unmapped page and it's a page fault. OS will bring the page back in memory, fix the page table, we'll restart the program, everything will go as nothing has happened, right? Asynchronous, where like it's a notification from an external device, so either from a timer, which periodically interrupts the execution of a current program, gives control to the operating system so it can may choose to run a different process, right? Because to enforce some fairness, and meaning that like it's simultaneously you may be like you're seeing all these windows, like my bars here, menus, my shell is running, right? Everything is running. So it's because we just switch very, very fast between them. And we will take a look at how context switch works so you will understand how it works. And a third special case, which you mentioned, is this. It's also synchronous, is when the program invokes an interrupt with a pre-configured number, in this case it's x80, to enter the kernel, to essentially implement a system call, right? And today, as I was saying, slightly better mechanism is available, which is called the cs5460. But in x86, we will cover this interrupt-based system call invocation question.
Have people considered making the syscalls asynchronous and synchronous?
Okay, let's discuss for a second. So how do you think you will benefit from an asynchronous system call?
Then I could issue a system call, do other operations. Or
correct. Okay, so normally when you say, I want to read a file, the expectation, naive expectation, is that you want to read it right now. Like when you program to your own, whatever, tiny little programs like cat, there was like fread or just read, right? And you say, look, I pass a file descriptor, a buffer, and the size of this buffer, right? And I say, just please give me this buffer back, right? And then I will do something to it, right? And this was a default implementation, meaning it's like a function invocation. And if it's fast enough, you don't have to worry about anything, right? But imagine this read takes forever. Maybe it takes like 1,000,000 cycles, and it does really take 10 million cycles if you're reading from this, right? If you're not hitting the buffer cache. So then you say, okay, maybe it's worth doing something else while I'm reading the disk, right? So as a software developer, so someone will tell you, okay, guys, yeah, we got it. So what you do is you create one thread of execution to do the reads, and maybe some other thread of execution will do something else. And periodically you will check whether this read completed, right? So that allows you to kind of like do something while this read is processed, right? Not surprisingly, people started thinking about the question, can we do this system calls asynchronously? And it was tried many times, right? So I tried one as well. I have a paper about it. It's like semi-successful, I guess, but people tried more. Like you can say read, and this read actually executes on a different core of a CPU. There are some additional benefits from like not polluting the caches of the current CPU when you switch it and do the read, but just send a message to a different core, and then the read happens there, and then it returns back. It was tried again recently when we were trying to address meltdown attacks, because this switch of a page table, this kernel page table isolation, KPTI, let me just write it down for you so you remember this, KPTI, was so slow that those asynchronous system calls to a different core, even though they exposed the synchronous interface, just avoiding the switch of a page table was much faster. So it was tried, but programming asynchronous things is hard. That said, like if you have some nice language wrapping around it, like we talked about continuation, but I never came back to explain what's the difference between continuation and what? I forgot, lambda or something. And languages can make this asynchronous programming sane, but in many cases it becomes quickly insane, because it's hard to reason about which events completed and which haven't yet. So people don't like it. But that said, the fastest disk interfaces like NVMe, they are so fast that even doing a system call is a burden. So it's like you lose performance, and you really, these days you have an interface which allows you to submit a bunch of requests like a batch, and then later pick them up. So which is asynchronous, and you don't have to wait for completion. You just say submit. Later on you say what's completed, and you pick up those results. So there is this variety of choices which you can make to optimize those interfaces depending on the constraints. Okay, any other questions? I mean, it's a nice topic for an advanced OS class, so we're still in just an intro to OS. Okay, let me go dive into those details. Remember, I just wanted to bring it back, kind of swap it into your memory, right? How we process interrupts, right? So remember my wonderful fetch, decode, register, read, execute loop, right? CPU normally just executes instruction by instruction, but on every iteration, it actually checks whether there was an interrupt, right? And normally everything goes as planned. You know, you fetch, decode, register, read, execute. The fault is actually a synchronous interrupt, right? And if it happened, you actually go to the exception handling here, right? So this is like a page fault, because maybe you accessed the memory which was not mapped, right? So if it didn't happen, you commit the instruction saying, okay, this result will become permanent. You generate the next instruction pointer and you move forward, right? But again, on every iteration of this loop, you check, okay, maybe there is a synchronous interrupt from hardware waiting for me, right? And then if yes, I will process it, right? So CPU doesn't process like literally, like it doesn't happen immediately. The CPU does a little bit of work. It can finish, like, okay, CPUs are complicated. There's like, again, out of order execution internally. So it's not just a single instruction. There's a bunch of instructions are executing in parallel, right? But nevertheless, you're always checking, right? Roughly speaking. And you say, look, if exception happened, if the interrupt happened, the CPU will switch. And the switch is what we will cover like in the next couple of slides. But literally, the high-level idea to understand here is that CPU doesn't suddenly switch to some like completely different execution mode. It just changes the instruction pointer, right? So it just, what happens here is that it saves a little bit of a current information, so it can resume execution from the currently executing instruction. It locates the position in memory of the current of the interrupt handler, right? So literally, we were executing here. That was our instruction pointer, some instruction from user memory, for example. The CPU says, okay, there is a mechanism for how to figure out what to do on interrupt. And it's just the same memory. So like maybe it's some of it is user, some of it is kernel, but this is the same, like essentially same instructions are sitting here. You're just changing the instruction pointer. And the CPU just sets the instruction pointer to point to the beginning of the interrupt handler, right? And maybe the CPU switches the stack. And I will explain why in some cases it's important to change the stack, right? Because it's unsafe to continue on this user stack. And again, the CPU, since you're changing the instruction pointer and the stack pointer, you have to save the old versions, these two, you have to save them somewhere, right? In order to be able to resume this old execution later, right? So it does save the stack pointer and the instruction pointer. And it actually happens to save them on this new stack, right? We'll cover it again in a second. And then essentially initialize your stack pointer and instruction pointer to point to these new values. And at this point, just back to this fetch, decode, execute loop, right? Because this is the transition, but we want to reuse as much of the CPU logic, this highly optimized logic of fetch, decode, execute, right? And execute interrupt handlers on the same kind of hardware, right? So we just did the switch and we start executing interrupt handlers. And again, the high level point here that interrupt handler is just the same code in memory. So it's the same function, which you can, roughly speaking, write in C with just maybe a little bit of assembly because you will have to save the old registers, right? But it's just the same, right? Any questions about this high level idea? Okay, good. So this is what my CPU starts executing now, this code. Okay, as I was saying, handling interrupts, asynchronous interrupts, and synchronous interrupts, like on this figure before, is just the same. If I clear everything, so if this is asynchronous, interrupted by the hardware, or this is a synchronous one, which like maybe it's a division by 0 or an access of a unmapped memory, it lands on the same procedure, right? So it's roughly speaking the same logic, right? Okay. And at a high level, as I was saying, what happens is we stop execution of the current program and start execution of the exception handler. And the question is like, where do we get this handler from, right? So again, the hardware has yet another table, which is called interrupt descriptor table, which the operating system configures, right? So it's again, array in memory. And we'll take a look like at this array in a second, and a hardware register, which holds the pointer to the beginning of this array, right? And then an interrupt has a number. So for example, number 2, for example, if this is 1, 0, 1, and 2, if you say something like int 2, or your timer generates int 2, the hardware will say, okay, I will look at the entry in this array, and this will help me to locate where the exception handler is in memory, right? So for example, 14 is a page fault, interrupt 3 is a debug interrupt, which allows you to single step programs and stuff like that, right? And this is simply an index in the interrupt descriptor table. There is, however, a little bit of a complexity here. So there might be two cases. The case number 1, which we consider first, is when the interrupt requires no change of privilege level. I still did not explain privilege levels very well. I will explain the privilege levels by the end of this lecture, maybe not today, but by the end of this slide deck. So you will fully understand what these privilege levels are. But just trust me for a second that this is the mechanism which allows you to distinguish user code from kernel code, right? And in case you're already running in a kernel, so CPU runs already in the kernel inside privilege level 0. So there will be 4 privilege levels, 0, 1, 2, and 3. And 0 is the most privileged. This is where the kernel is running. And 3 is the least privileged. This is where the user programs are running. And these two are rarely used, but sometimes they are used.
Unless you're in kernel, where do you define the code?
It's saved in some hardware register, so we'll come back to it in a second. So I will explain it kind of well in a second, but just believe me that hardware keeps track of the current privilege level. It knows that you're running in a kernel, or it knows that you're running in user, right? And if you're already running in a kernel, then when the timer interrupt arrives, for example, kernel tries to access an unmapped page, just because we're so smart and we build the kernel which can page out itself, right? So which is not happening in x86, but Linux does it, for example. Then you don't have to change, you stay in 0. However, if you're running at user at privilege level 3, when an interrupt arrives, intuitively you want to switch back to the kernel. And this is how the system call also works, right? So if you invoke a system call, you switch from 3 to 0, right? But even if you want to process a timer interrupt, definitely you want to process it in the kernel, right? Because the kernel is the one which makes the decision which program will run next, right? So in this case, you have to switch from 3 to 0. So let's first take a look at this case where we don't switch the privilege level. So the machinery of the interrupt is relatively simple, right? So imagine you're running in a kernel. You already have a stack, like this is your kernel stack somewhere in memory, right? And like some kind of a function, you got some arguments in, you have this return address, you save the old EBP just because you maintain the stack frame, some local variables, right? So maybe like some spilled registers saved on the stack as well. Overall, this is your stack. It grows this way, right? Suddenly, you have a timer interrupt. So timer interrupt is vector number 32. I will explain what this IRQ0, why it means the same as 32, but literally just entry 32. As I was saying, we have the table in memory, which is configured by the kernel, right? So this table, interrupt descriptor table, sits somewhere in the kernel's, let's say, either on a heap or in a data section, depending on how we allocate it. It doesn't matter, right? So somewhere in kernel memory, right? And what the hardware is doing, it says, okay, I will use this number 32, to locate an entry in this table. What is the reason why we need this table? Do we understand this point? Let me ask a control question to make sure that we're on the same page. So why we need this table? What's the role of this table?
Oh, it tells us where the interrupt handler code is.
Correct. So this entry will have a bunch of fields, but forget about those fields for a second. Mostly we use it right now to figure out this pointer. Essentially, where's the entry point to process the vector 32? So essentially the exception handler for the interrupt number 32, right? That's why we need this table. Okay, cool. So again, those are kind of the entries, right? So the hardware will maintain this interrupt descriptor table register, IDTR, which will essentially have a virtual address of the beginning of the interrupt descriptor table and the size of the table. And again, unless you're really initializing the interrupt descriptor table, just at a high level, it's a pointer to where the table is in memory and the size of the table, right? And the operating system configures it, and we'll take a look at how we do this, right? Okay, cool. So this is nice. And again, just to make sure that we separate them cleanly. So this is the register. So it sits on the CPU. So CPU is gray, and the table sits in memory, right? So memory is awkward yellow here, right? Okay, cool. So the entries, again, numerous entries. This is one entry in the table, one of these, right? And there's a ton of fields, which again, we can go one by one, but we're not gonna use them immediately. What we really care about is just this offset, right? So it's literally 32 bits, sorry, let me erase. 15 bits here and 15 bits here. And together they like it's a pointer which can point anywhere in a 32-bit memory. That's the beginning of the handler, right? The entry point of the function which will be responsible for processing the interrupt. Again, as I was saying, those interrupt handlers is just the same plain old C code. So don't get surprised. So same instructions here, right? And we will take a look at how, like, details of how these handlers are implemented next time. But again, so nothing super special. However, remember when we looked at this fetch, decode, execute loop, I said that we have to save a little bit of state. So what state we need to save in order to resume execution of the program before the interrupt? So really, what is immediately changing when we process the interrupt?
You've got it on the board, flags, the stack pointer, and the instruction pointer are all going to be changed.
Got it. So, but let's just, I have it on the board, but just logically, like from my figure, since we're changing the instruction pointer, so really we're using the value of the instruction pointer. So we have to save it immediately, right? It turns out that for historical reasons, because we used to build systems around segments, not around page tables, we also have to save the code segment, because I said that we don't care about other fields, but really in this table, and I'm just trying to scroll backwards, you are allowed to pick a different code segment. And it will become clear why it's needed for when you switch privilege level, but you can actually do that in other cases as well. Right? Okay, so this we have to, let me just mute my phone. This we have to do, right? So these two, this is clear, right? This is totally logical. We say, okay, like clearly AAP is gone and code segment is also maybe gone, right? So why do you think we have to save flags? Flags register, E flags. E stands for 32-bit version of the flags register. Who can guess? It's a little bit unusual.
Well, it interrupts. Maybe I've got my code going on and does compare these two numbers. The very next instruction is going to be jump according to the comparison, and an interrupt comes in between those two. I need to be able to keep those flags between those two as that interrupt gets in.
No, but if you have a vector 32 label in assembly, nothing prevents you from saying push E flags here, which means that that will be fine, right? So you don't need a special like handle it in hardware if you can do it in software, right? So keep it simple kind of principle. But something is happening to the E flags register in hardware. So what can happen? I just want to make sure that I kind of clarify why we save each thing separately versus like just like giving you this information.
Is it because when you're going to run the next instruction, if an IF flag is set, then we think, oh, there's another instruction?
Exactly. So what you're saying is the following. So the hardware provides you a way to say, in this interrupt descriptor table, you can make a choice whether you want to disable further interrupts or not, right? And if you really, and it depends. Like sometimes you say like, if it's a system call, well, maybe it doesn't make sense to disable interrupts from network interface because I really like trying to implement a function call. I want it to be interruptible. But if it's some kind of an interrupt which came from the device, maybe from a timer, and maybe at this point it's very inconvenient to handle yet another interrupt, you can say, okay, like the moment the first interrupt happens, other interrupts are disabled or deferred until explicitly re-enabled. And if you remember, the way on x86 to disable interrupts is to set a bit in this eFlags register. And literally, you can configure in this table to say, change this bit. But if you configure to change like this, to disable interrupts on entry through an interrupt descriptor table, you need to know the old value of the eFlags because you want to restore it, right? And that's why the hardware saves eFlags as well, right? So right now, only 3 things have to be saved, nothing else, right? We stay on the same stack. And this is the only 3 things which the hardware pushes on the stack, right? So literally, if your old stack was here before the interrupt, the hardware pushes the 3 things, and some additional interrupts and I forgot exactly which ones, add a specific error code when they are delivered. So maybe like an exception handler will push an error code, which I should admit I don't remember. I've seen it many times. I don't remember exactly. We'll come back to it like next week for sure. Like, but believe me, trust me. Actually, yeah. Okay, cool. So definitely 3 things are saved, and this 4th thing is saved by some interrupt, but not by all of them, right? Okay, cool. So this is reasonably easy. We kind of still can follow. And as I was saying, those things are saved by the hardware on the same stack, which I was using here by the kernel. Like kernel uses the stack. So this got pushed by the hardware. Instruction pointer is changed to the entry of this, like the first instruction of this vector 32, and the CPU will start executing code here, right? Reasonably simple, right?
ESP, why are we not storing ESP?
Because we continued running on the same stack, so ESP is set to be here, right?
But this is a different stack, right?
No, it's the same stack.
So we're storing all of them in user stack.
On this kernel stack, we are just immediately just moving. ESP is updated to point to this address, obviously, right? But when we return from the interrupt, we will just invoke a special instruction which is called IRAT, which will pick up those values, restore them in registers, and ESP will be restored back to this value like nothing happened, so everything is fine.
What about the user process memory?
We'll come back to it in a second. This is the case when the interrupt, when the privilege change is required. I think I will cover it today.
What about every process will have IDT, or for all of them will be having only single IDT, which is maintained by kernel?
It can be, it's a design choice, but typically one IDT is enough per CPU on modern machines. And we'll see how the x86 initialized the interrupt descriptor table maybe next time, but I will show you the code, and you can, like, I'll ask you those questions, like how many IDTs are there? I mean, I think it's 1 for all CPUs on x86. Linux does, I think, IDT per CPU for scalability reasons, because there's like a trick to make sure when devices are so powerful that there is an idea to dispatch specific network queues. That's the queues which I was drawing. Typically, devices have multiple, and you say each queue belongs to one CPU, just because then there's less shuffling between CPUs, less coherence traffic. We'll come back to coherence and problems related to coherence later in the class.
When you say per CPU, are you meaning like per CPU core, or like hyper-threading the half, or whatever you want to call that?
No, like,
or for like
right, for like modern systems rarely distinguish hyperthreads from cores, because hyperthreads pretend to be cores. And so typically Linux will treat a hyperthread as a core. x86 will do the same. So when we might go back and look at how the cores are initialized, and each hyperthread will pretend to be a core. So it's per this, although you can make different design choices, really, but typically at least per core, and sometimes maybe per CPU thread, per hyperthread as well. But here in x86, I think there will be just 1. Okay, good. Okay, so this we understand. Okay, how do we return from the interrupt? Instead of doing a ret instruction, which, remember, ret just simply picks up the instruction pointer from the stack, right? If you have a return address on a stack, right? So this IRAT restores 3 things, right? Because we saved 3. So it picks up the instruction pointer, code segment, and eFlags register, right? But the logic is the same. So it's kind of like return from a function, just a special one, and just can restore this stack code segment as well. Good? Not so hard. Now the second part of my story, when we need to change privilege level. And this is specifically is interesting because this is the first time when I will explain what these privilege levels are like. And again, it kind of connects to why I was teaching segmentation, because many classes don't teach segmentation at all. They just say, okay, here's the page table. Privilege levels are kind of amorphous. They exist. Like, someone will explain what they do, but no one will tell you how they are implemented. But I think it's still relevant. And just to make sure, like it's the x86 hardware is a little bit ugly, and again, backward compatibility reasons and stuff like that. But nevertheless, let's take a look. Okay, so this is a question. So can a process overwrite kernel memory? Obvious answer, no. We all know now, right? And if I ask you, how do we enforce it? Who can tell me? How is that enforced? The fact that the user level cannot write into kernel memory. Paging? With page tables, right? Okay, so clearly I mark my green pages, user pages green, kernel pages yellow. I construct a page table. Some of those pages will be mapped through those green mappings. Some will be mapped through through yellow. Okay, cool. So nevertheless, what is this privilege level? Each segment has a privilege level. It's called DPL, descriptor privilege level. This is this field, which is 2 bits, which can encode any value from 0 to 3, right? So 0, 0, 1, 1, 0, and 1, 1, right? So, okay, it's a little bit ugly because, okay, what are those descriptors, right? So really, like, again, you're talking about them. Just a reminder, right? So this is how the hardware works. And unfortunately, you cannot disable this first part, right? You know, remember logical address, 2 parts. So there is the segment selector, which is, for example, like data segment or a stack segment or a code segment, right? Which is encoded somehow funky, but what we really care about is the number, right? And this number lands us on the entry in the global descriptor table, right? Okay, cool, we got what this, and this is where the segment descriptor, which I shown on our previous, which I showed on the previous slide is, right? And this, we normally, I just said we take a base and a limit from this, but there is something else to it, right? There's actually, it has this DPL here, descriptor privilege level, right? Okay, and this is essentially a mechanism to like allow transitions between privilege levels. I will explain in a second. So there is also a notion of a current privilege level, or a CPL, which is tracked by the CPU. So when you're executing the code, you know at which privilege level you're running, right? And again, it's the same from 0 to 3, right? And roughly speaking, it's saved or defined by the code selector register. So essentially, when you do CS, remember this logical address, CS plus some offset, right? When CS lands you on the global descriptor table, right? You read this field, DPL, and maybe it's 3, or maybe it's 0, or maybe it's something else, 1 or 2. And this 3 defines that you're running at level 3, right? When someone did this long jump and picked an entry into GGT, which is 3, then you're running at 3, right? So this is where you configure, roughly speaking, configure the distinction between user and kernel code. I'll get to it in a second, just bear with me. So this field is loaded when the descriptor for the currently running code is loaded with like this code segment register. It can be loaded, remember we've seen long jump when we switch from 16 bits to 32 bits, right? It can be loaded with IRAD, because remember, IRAD restores the code segment. So when we do IRAD, we can say, okay, like please use this code segment, and maybe we'll pick the one which has 3, or maybe we'll pick the one which is 0, right? Okay, like a little bit of a background on this current privilege levels, or in general privilege levels. So again, 4 entries, 0, 1 to 3. 0 is the most privileged. So 0 is where the kernel is running, and 0 can access 1, 2, and 3. Naturally, 1 can access 1, 2, and 3, but cannot access 0. So it cannot just simply say, I can read memory of 0. It can read memory of 1, 2, and 3, or do something, transition back into 2 and 3, or back into 1, but cannot transition into 0. And 3 can only access 3, right? So this is user. And kernel, 0 is kernel. And some instructions are privileged, meaning that they can only be invoked at current privilege level 0. Actually, maybe this is a bug. I should check it, but maybe at 1 and 2, but definitely not 3. Maybe the first 3 levels are privileged. We have to double check that. And why is that so? Because those instructions, which allow you, for example, to load a global descriptor table, they immediately break the isolation model, right? If you can change where the global descriptor table is in memory, you can control the whole system. Or, for example, if you move something in a control register, kind of do a move into CR3, changing the base pointer of the page table, you again can control the whole system, because you say, look, suddenly, if you change the GDT, on the next transition, you say you switch not from 3, but switch to 0, and you control everything, right? So some of these instructions are privileged. They can only be invoked by the kernel or by privilege level 0. And if the user code tries, if you're running at CPL3 and you try to invoke move into CR3, you immediately get a protection violation exception, right? So this is to enforce integrity of the model, right? Okay, so how, with that knowledge, how did we end with a specific CPL? Again, when we were booting x86, there was no CPL yet. We were still in 16-bit mode. Segmentation was not yet enabled, right? So you can access any memory at this point, anything, right? Any physical memory, but you only have 16-bit of address, so not much, only 64 kilobytes, right? Then we say, okay, we're gonna create a global descriptor table, and we'll do this long jump. We will use entry number 1 in this GDT, right? So remember, we first loaded GDT to GDTR register to point to this table, and this is where we enabled segmentation. And by controlling the descriptor privilege level in this entry 1, we set the privilege level. If we suddenly say, instead of DPL 0, run at 3, it's a good exercise to see at what point you will crash, right? Or what instruction will not be executed correctly. But we were smart, and we said, okay, DPL 0, so meaning then when we jumped, we immediately jumped to level 0, so we're fully privileged, right? We just retain all the rights, right? Clear? And so obviously, that was making sense. Why not? And again, the way we did it is that we set this DPL field to be 0. We never seen it really, we didn't deeply track how we did it, right? But let me show you. So this is how we initialize this global descriptor table. We use those assembly macros, and this field specifically controls, oh no, hold on, this is not the field. So this assembly macro, and if you look at the definition, it loads the DPL to be 0, right? That's how we did it, to make sure that I actually don't remember the definition. We can quickly again at this point, you can roll your eyes again. This guy starts looking at the code, but where did we do? Let's just quickly do grab of this ASM GDT. Is that how it's spelled? Seg ASM. Okay, sorry. And just to check the definition to make sure that we are correct. Got. So anyone wants to guess which field is which? Hard, right? Okay, I give up. At this point, one of these will set it to 0, right? But we have to investigate which one. Failure. But okay, maybe you can take it offline and do it yourself. Okay, but this is how it was done. Okay, so we're running at CPL 0. We're running the kernel, which means that we can initialize, we can run load CR3, right? So we can configure where the page table is located in memory. We're fully privileged, everything is fine, right? And the first time we're going to transition into user level code, it will become clear how we do that. When we do the very first IRET instruction, this IRET instruction, which we will invoke, which the kernel invokes after it initializes the first init process, essentially we'll choose an entry like code segment, and this entry will be configured with DPL3, right? And at this point, after you execute this IRET instruction, you kind of switch privilege level to 3. And you will start executing at privilege level 3 here. Big question.
why, for the data section for user code, why do we even put kernel memory for that? Why don't we just go 0 to 2 gigabytes?
We can. It's just that the question here is that why did we put 4 here instead of 2 gigabytes, right? It's just that we're so lazy that we say, like, we're going to control everything with page tables. So don't even bother. That's reason number 1. And reason number 2 is that on x86 64-bit machines, you can't even set it to anything but the max address. So they simplified the logic of the segmentation unit, saying, okay, no one uses it really, everyone uses page tables, so just forget about it. And you can't really do anything with this address. It's always FFF, whatever it is. Okay, so we kind of get this introduction to what happens when, like, how we actually switch to CPL3. So this is IRAT. You're running with inside user code, current privilege level is 3. And now imagine the interrupt happens. And this is what we're going to discuss right now for a sec, right? So transition of an interrupt from CPL to CPL 0, right? So back into the kernel, right? And you can either, like, it can be either a timer again, or the user can invoke this int with some number here and essentially trigger a transition back into the kernel. Okay, let's say, we still have like 7 minutes, so let's just finish it today. Again, just a slight comment. So as I was saying, kernel runs at privilege level 0, user code runs at level 3. Segments for both 3 and 0 cover everything from 0 to max address 4 GBs. And this is called a flat segment model. The reason is that, no one wants to bother about segmentation. Everything is controlled by the page table. But I wanted to come back to one important thing. So remember, the question which we asked at the beginning of this detour is, why is that the user cannot access kernel memory? So if I ask you this question again, so why? So what really blocks you? Like I said, there will be green pages and yellow pages. So what distinguishes green from yellow in terms of a page table? Privilege, but where is privilege? Is there a privilege in the page table? Correct. So one would logically assume that there should be a bit, like not a bit, but 2 bits, which say, okay, the translation is allowed according to this maybe privilege level rules, but you say, okay, I want to put a number here, maybe 3, maybe 2, maybe 1, maybe 0. Intel engineers, in their wisdom, said, okay, no, guys, nobody uses 2 and 3, 2 and 1. So just nuke them, and so which will save us a bit. And they just gave us 1 bit here, which allows you to distinguish only privilege levels 3, 2, and 1. Sorry, I think it's actually 3 and 2, 1, and 0. And those are the privileged, and this is user. So they just gave us 1 bit. And okay, so that we covered how we initialize the GDT last time. This was there. This is back to the question. So they gave us 1 bit. So remember, segments are flat. So page table has this user bit, and each entry at both in the page table directory level 1 or at leaves of the page table level 2 will have this bit. If set the coded privilege level, which is 3, can access this entry. If not, only levels 0, 1, and 2 can access, right? And I was saying that we only have 2 levels, not like 4, because they wanted to save this bit, right? So specifically, we set user bit for those green entries and don't set the user bit for the yellow entries at both levels. So here, and we set and unset it here as well, right? Both page table directory and in the leaves, right? And this way we say, okay, the segmentation unit doesn't really control it. We always set them to 4 GBs, right? But those segments do track this DPL. So essentially, when we switch between the segments, switch between something what is called privilege rings, right? We switch between 0, 1, 2, and 1, 2 are typically not used, but 0 and 3, right? With those instructions like long jump, IRAT, and int, right? Okay, so this is clear. This is why this is how the protection scheme is actually implemented in practice. Let me stop here for a sec. So any questions about back to this, like back to the question of why user cannot access the kernel. So if I simply teach the page tables, I will have to explain this bit somehow, but I don't have a way of explaining how we track this bit. So we track the bit through we track the privilege level through the global descriptor table.
I really have a question on that, more a question on like, if we don't use one, why do they exist?
Good question. So again, a little bit of a historical thing. So when those hardware designers were thinking about privilege levels, they said, okay, maybe the kernel will be running at privilege level 0, but maybe the OS designers are so smart that they will put the device drivers, which will be a little less privileged than a kernel, at level 1. And maybe they will be so smart that they will put something else, even less privileged, at level 2, and then we'll put something like user, which is the least privileged, at level 3, right? It makes sense because, like device drivers actually account for probably over 70% of the kernel code. There is roughly like over 3,000 device drivers in a Linux kernel. Who builds those device drivers? Well, I'm an employer, like I'm Qualcomm. I build a new cell phone, new whatever, tiny broadband modem, and I will have a device driver to run against it. Or I'm a GPU developer, develop a GPU graphic card. If I want it to be used, I will have to deploy a device driver as well, right? Because no one else will build the device driver for me. So Intel builds device drivers for their devices, Qualcomm for their devices, right? It turns out that those people who work on those device drivers, they are distributed all over the world, Asia, Europe, US. And it's our largest distributed development model. And at this point, no one really understands what the kernel is doing, what the security model of a kernel, and how to build a device driver in such a manner that it's really safe and secure. So device driver today are responsible for probably, like again, I keep saying roughly again, 70% of vulnerabilities, because the kernel is relatively stable, but with every new generation of hardware, you have a new device driver, right? So it's very easy to make a mistake. So putting device drivers outside of the kernel is actually a good idea. However, remember those old dudes who are sitting there, this PDP-11, they designed Unix and they said, okay, well, we're not that smart. Plus, we don't even have the C language yet. So we just forget about it. We'll put everything in a kernel as we do this in x86, right? So today we run x86. Linus Torvalds said, okay, well, I don't like those other dudes, but I will build my own kernel and I will become famous and rich. And not rich maybe, but famous. And he built the kernel in the same way. It's just better, but still the same. Some other people, remember I was mentioning this Andy Tenenbaum, who was responsible for this code which was running inside Intel management engine. He said, okay, you guys are wrong, clearly you're wrong. So we have to put the device drivers outside of the kernel. But it was so expensive, this transition between privilege level was so expensive that people who wanted to deploy things in practice, they said, okay, no, it's prohibitive. And so no one did it for a while. But then, the history kind of repeats itself. And, today we have teams, government-supported teams, which are trained to attack, infrastructure of another country, for example, or just attack your personal computer to get your credit card information. And so people are again scratching their head and saying, okay, maybe it would make sense to really move the device drivers outside of the kernel because it's such a big issue, right? Or build them in Rust or something. And so Intel said, okay, we're going to give you privilege levels. For 30 years, no one uses them. Intel says, okay, well, we're tired because we have to formally verify and test that our implementation is correct. So they said, okay, forget about them. And they transitioned to a 64-bit mode. They knew them. So we don't have them anymore. But again, now we're struggling to figure out how to move device drivers outside of the kernel to make sure that the systems are more secure. That's kind of a historical perspective. Any other questions? And I will let you go. Oh, man, 2 questions.
So just trying to understand what you just said. So in contemporary operating systems, what we're using right now, whether it's Windows or Linux, are the device drivers all running in with kernel privileges still?
Correct. Yeah.
Okay, so it's a big security moment.
It's a big security problem.
And sorry, just to clarify, so the reason why this works is because the user doesn't have access to the global descriptor table.
Right.
So that would be quite easy.
Yeah, because the moment a user can access the global descriptor table, it sets something like, oh my God, let's change it to 0.
Yeah.
And then the moment you return from an interrupt, you returning with kernel privileges. And at this point, you own the machine. Okay, so this is the end of the detour, and we'll come back and we will handle the case when we do have to switch privilege levels next time, and then we will continue with system calls on Thursday. On Thursday is again this 50th anniversary, so please try to, I mean, I think it's worth it. There will be a live stream. The people who are coming to give talks are just heroes of their time. So just make sure that you attend at least some of them.
What does the DPL of the data session do?
Say this again.
The data segment, it also has a DPL, right?